Hello friends, welcome to Susan and John MathTube. In this video, we are going to continue our discussion on Gauss Divergence Theorem. And in this video, we will be dealing with the sphere problem. So, I hope you watched the last two videos. In the first one, we discussed about the cube. And if you understood the cube, I am sure that by checking any reference book, you will be able to understand the cuboid and the parallelly piped. And in the second video, we learned how to deal with a standard right circular cylinder. Okay, and I gave you one more problem so that you can practice. And now we deal with a spherical surface. Okay, so we have to verify Gauss Divergence Theorem for the surface integral f dot and ds, and f is given to be, you can copy it, yz into I plus zx into j plus xy into k, and the surface is x equal to 0, y equal to 0, z equal to 0, and x square plus y square plus z square equal to 1 in the first octant. So, this is a closed surface, so we can apply Gauss Divergence Theorem. So, always remember, we can apply Gauss Divergence Theorem only in a closed surface. Okay, so as always, I am going to write the statement: double integral f dot n ds is equal to triple integral divergence of f dv. Okay, and I told you one more thing. In my videos, I never kept surface integral and volume integral separately, because when we learn Gauss Divergence Theorem, we are doing the verification. So naturally, you are getting a skill how to evaluate the volume integral and the surface integral. Okay, so let's go to the graphing calculator. So I have already constructed the region. So I think you can see x equal to 0. X equal to 0 means the yz plane. Y equal to 0 means the zx plane. Can you see the planes? The three standard planes. And I'll show you the full sphere also. I hope you are able to see the sphere. Now, this is the first octant. Can you see? It's slightly differently colored here. So, this is the first octant. So, we are not interested in. Are you able to understand? We are cutting the sphere into 8 parts. 1, 2, 3, 4 on the top, and similarly 4 on the bottom. And they have clearly given the surfaces. Okay, I will do one thing. Okay, I have removed it. So, you have to understand, this is our surface. So, you can see that when I say the word surface, you should remember closed surface. So, this is the curved surface, and here we have a flat surface, and here we have another flat surface, and from the bottom also you can see. So, can you see 1, bottom 2, 3 and the curved surface. So, 3 flat surface and 1 curved surface. If you are not able to visualize, I will strongly recommend take a big lemon or a spherical potato and cut it into 8 parts and keep 1 part. Or you can imagine we are cutting a watermelon. We are cutting a watermelon into 8 parts and we are keeping 1 part, 8 equal parts. And you will be able to see there is one curved surface, that's a blue part over here, and one here and one below. So, there will be total 4 surfaces and 1 volume. So, we are going to evaluate 5 integrals here. Okay, so let's go back. So, let's do it very fast. I always love to evaluate the volume integral first. So, I am going for the right hand side. So, if I want the right hand side, I have to calculate divergence. And you know how to calculate divergence. partial derivative with respect to x, the I component, plus partial derivative with respect to y, the j component, plus partial derivative with respect to z, the k component, and I got a surprise here, it's going to be 0. Look, we are differentiating with respect to x, but there is no x, and similarly, the answer is 0. So divergence is 0. So that means the right hand side, that's a triple integral, divergence of f will be 0. Okay, so once more let me tell you, I made a rough picture. Look, this is the problem when we try to plot a 3-dimensional picture in a 2-dimensional screen. See, but I hope you are able to understand. I am talking about the flat surfaces OAC, OBC and OAB. A means point on the x-axis, the blue axis, and B means the point on the the green axis, the y-axis, and of course the z-axis is C. I think I'll show you the other one, that will be much, it will be more visible. So the origin is O, the point on the x-axis, the red one is A, the point on the y-axis, that is B, and the point on the z-axis, that is C. So remember, there are 4 flat surfaces and 1 curved surface. I am going to deal with the quarter circle. Can you see? Not semicircle, quarter circle. Are you able to see? This is O, A, C. O, A means on the x-axis, C means on the, So I am going to write a double integral surface is equal to double integral S1 plus double integral S2 plus double integral S3 plus double integral S4. So this means I am going to take O, the point on the x-axis, the point on the z-axis. And then my second circle will be O, the point on the y-axis, point on z-axis. And the third one will be O, point on x-axis, point on y-axis. And then the last one, the curved surface. Okay, so I wanted to show this picture once more. I hope you are able to see. My x. Let me change color to green. So look at this. The red axis is our x-axis, green is y-axis. And now we are able to see our OAC. And since it is a quarter circle, it's a plane figure. And can you see the outward drawn normal is? Are you able to see that? The outward drawn normal is minus j. Are you able to see? This side is the first octant. So this is minus j. Just try to imagine. Once more let me tell you. This picture is in the first octant. This picture is in the first octant. So this is the positive x-axis. This is the positive y-axis. And this is the positive z-axis. So if you look at the flat surface, the quarter circle here, are you able to see? O, A, C. Then the outward drawn normal is minus j. So I am going to write that for surface 1, n cap is equal to minus j. And you can notice one more thing, y is equal to 0, because that's the xy plane. And you can understand one more thing, and ds means that will be ds1, ds1 will be dx dy. I'll show you that in the graph. Look, y-axis means the green movement, but you can see that in this part OAC there will be no green movement. You can go up or you can come towards in the red direction. So basically it will be dx dy. So that's it. So let's find f dot n cap, and that will be yz into I plus zx into j plus xy into k dot minus j. I told you we have an advantage when you take dot products with the standard unit vector. So you can forget about I and k, you can focus here, the answer will be minus zx. Now look at this. The region, like what you call, this is the region O, A on the x-axis, and this is our blue axis, so this is our C. So you can see that here y will be absent. So this circle is actually given by x square plus y square equal to 1. Y will be absent. So I can say that if I make a strip, x varies from 0 to 1. It's a unit circle, right? So x varies from 0 to 1, and y varies from, y is 0 actually, z varies from 0 to root under 1 minus x square. You can find that z value from here. So double integral S1 f dot n cap ds is given by x equal to 0 to 1, z equal to 0 to root under 1 minus x square minus zx dx. Oh, what did I write here? It's not dy, dz. I told there is no y moment, so please do correct it. There is no y moment, it is z. So I should write dz dx because the inner limit belongs to z. So that will be x equal to 0 to 1, and x is a constant, minus goes outside, so x into z square by 2, z equal to 0 to root under 1 minus x square dx, and that simplifies to minus 1 by 2 goes outside, x equal to 0 to 1, x times, when you plug in the upper limit it becomes 1 minus x square, and when you plug in the lower limit there is nothing. So that will be minus 1 by 2 into x equal to 0 to 1, x minus x cube dx. It's not a big deal, you can integrate, you will get minus 1 by 8 at the end. Now let's look at the next region, S2. S2 means the region O, then you connect it with the y-axis, then you connect it with the z-axis. So that will also be what you call a quarter circle, since it is connected with the, like what you call, since it is connected with the y-axis, I am going to color it green, and since this is connected with the, I am going to color it blue. So remember, this is the z-axis, so there is no x moment, and the outward run normal will be minus I. I'll show you in a minute. And the limits of integration will be, this is the y-axis, y varies from 0 to 1, and z varies from 0 to root under 1 minus x square, because the circle will be, x will vanish, so y square plus z square equal to 1. The total circle was x square plus y square plus z square equal to 1, but x will not be there, right? So it's like y square plus z square equal to 1, so z will vary from 0 to root under 1 minus y squared. Okay, I'll show you what's happening in a minute. Look, so here we go. Can you see? Green means y-axis, blue means z-axis. So you can see that the outward drawn normal is our negative x-axis. Look, the outward drawn normal to this plane surface is our negative x-axis. So n cap will be minus I. So n cap is minus I, and there is no x movement, and the surface movement means you can move in the y direction, you can move in the z direction. So again you calculate f dot n cap, and this time you are going to get the same value, like what you call, it will be minus yz. You can evaluate it, you can try to evaluate the integral just like before, integral S2 f dot n cap ds2, and the answer will be minus 1 by 8. And what will be the third circle? The third circle will look like this. This is our z-axis, this is our y-axis, and this is our x-axis. So the third circle will look like this here. it's a quarter circle over here, and you can see that there is no height movement, and the unit normal will be minus k, because this surface is the bottom portion. So this is A, this is B, this is O. So surface S3 means OAB, and this circle will be given, so there is no Z. So the sphere becomes the circle x square plus y square equal to 1. So x varies from 0 to 1 and y varies from 0 to root under 1 minus x square. And as usual, you do the integration double integral S3 f dot n cap ds3, and you will get minus 1 by 8. So we got minus 1 by 8 3 times. Okay, now the main part, the curved surface S3. Wait a minute, I'll show what's happening. Look, just now I was pointing towards this surface. Can you see the bottom? This is our A. On the red axis, the x-axis, it is A. On the green axis, it is B. And look, the outward drawn normal, can you see? Minus K, minus K. Okay. Now let's go for the last surface. It looks like an igloo. So the curved surface. The problem with curved surface is the unit normal vector will not be same. So for the curved surface, we have to calculate n by calculating gradient of the surface. So the function is x square plus y square plus z square is equal to 1. I'll make it a function by taking everything to the left side, which you learned long back. So it's very easy. I partial derivative with respect to x plus j partial derivative with respect to y plus k partial derivative with respect to z. And then I'm going to make this a unit vector. So you write the same stuff on the numerator, and denominator we will take squares of the components and add them up. And if you take common, you can see that it becomes 4 into 1, because x square plus y square plus z square equal to 1, and it comes outside at 2, and finally it simplifies as ix plus iy plus iz. Now let's calculate f dot n. F dot n is yz into I plus zx into j plus xy into k dot ix plus iy plus iz, and that gives, you know what to do, right? xyz, 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 we get 3xyz. And another thing, when you evaluate a curved surface, you should always project that surface either on the xy plane or on the yz plane or on the zx plane. So anyway, I'm going to project this surface on the xy plane, and you know the projection will be a quarter circle. So always remember, whenever we deal with a curved surface, to evaluate the integral, we should project it on the xy plane or yz plane or zx plane. So I'm going to use the formula for xy plane. So my integral s for f dot n ds will become, f dot n is 3xyz, and here what happens, we will get dx dy divided by mod n dot k. And what is n dot k? N is here. N dot k will be ix plus iy jy, oh this is j and this is k, plus kz dot k, and that will give us z. So we get double integral 3xyz dx dy by z. Okay, now you have to look at the projection. The projection is actually, the projection of the curved surface is nothing but our quarter circle. So I know that x varies from 0 to 1 and y varies from 0 to root under 1 minus x square 3xy dx dy. Of course, you have to write dy dx, and I'm not showing that integration step. If you integrate, you're going to get 3 by 8. Okay, now let's go back and look at this. So what will be the surface integral? Minus 1 by 8 plus minus 1 by 8 plus minus 1 by 8 plus 3 by 8, and that gives 0. So that's it. It's a little bit confusing. So I'll be back with I'll try to be back with one more. I'll be back with one more video, and I hope you'll get a better explanation there. So the only thing you have to be very careful is, be very careful when you are dealing with curved surfaces. When you want to evaluate a curved surface integral, you have to project it into the xy plane or yz plane or zx plane and evaluate the integral. So I'll be back very soon. So till then, my friends, bye.